doubly linked list. So normally when we say linked list, it is singly linked list or single linked list. Generally it is called as singly linked list or single linked list. Here what this single double indicates is the number of pointers that are associated with a node. Normally when you take a single linked list, there will be data, there will be pointer to the next node. There will be data, and pointer to the next node. This is how the singly linked list will be built. And the last node, the link or next field of the last node will be null. So the problem with this single linked list is we can traverse in only one direction. Traverse in only one direction. One direction. So this is the biggest problem of single linked list. Now, if I want to traverse to and fro, now suppose here in single linked list, suppose if I have a address of some middle node, I cannot access the nodes that are present before that. So that is the problem with single linked list. We can traverse in only one direction. In doubly linked list, what happens is we can traverse in both directions because there will be two pointers present. One will be pointing to the next node in the linked list. Another will be pointing to the previous node in the linked list. That's why the name doubly linked list. There will be two links. One which will take you in forward direction. Another which will take you in backward direction. So there are two pointers associated with doubly linked list, so that if you have a address of a node, you can reach any other node, and also we can move either in forward direction or backward direction. So to allow the movement of the node in both directions, so the movement of the linked list in both direction, every node in the doubly linked list will be having three fields. One is data field, another is pointer to the next, and pointer to previous. So there are three fields present. Next points to the next node, and the previous points to the previous node. And next field of last node will be null. So next of last node, and previous of first node will be null. To indicate that after last node there is no other node present, and after first node, before first node, there is no other node present. So the next field next of last node and previous of first node will be null. So this is how the doubly linked list is built. So because of the two pointers, we can go either in forward direction or backward direction. But the important thing is each time you do any operation related with linked list, especially insertion and deletion, we have to take care of both pointers. Because suppose if you insert in the middle, we have to modify previous pointer, modify next pointer. If you delete a node somewhere in the middle, you have to modify both the pointers. So you have to be careful in dealing with doubly linked list because here there are two pointers. So both the pointers you have to update each time the doubly linked list gets some kind of modification like insertion, deletion kind of thing happens, then we have to take care of both the pointers. So normally if you take the doubly linked list, because of the flexibility in moving both direction, it is very frequent. It will be used very frequently with respect to the single linked list because the traversal can be in both the directions. Now, when we take, this is how, so if I take one particular doubly linked list, suppose if I have some nodes like suppose 10, 20, 30, something like this. then will be pointing to this will be pointing to this, and this will be pointing to this. This is pointing to this. This is pointing to this, and this will be null. This will be null, and this will be null, and there will be start node. Sometimes what we can do is we can also have left and right nodes, but it is up to the requirement. So we can use pointer to the first node, which we call it as head node or start node. That's how it will be there. Suppose the address of this is 1200, address of this is 1000, and address of this is suppose 1800. So 1200 will be present here, and 1000 will be present, and 1800 will be present, and 1200 will be present. So the previous field of first node and next field of last node will be null. And if you want, you can also have two nodes, like there can be last pointer or last or end node. You can say you can have end pointer to the last node and pointer to the start node. But as per the requirement, you can have whichever pointer you want, but at least there should be pointer to the first node. So this is how we manually represent. Now, before we proceed with the representation in C structure, which is almost similar, suppose if I have to insert a node here. So if I have to insert a node here, so reach here, this node, take this node, suppose assume that this is the current node. Now I want to insert this, suppose 25, and I have to insert in between these two. I have to insert here in between these two. So what we can do is, this is assume that this is new node, P node, new node. This is P current. You are here. So now if I want to insert here, what I have to do is store 1800 here. Store address of this node here, because now what you have to do is you have to make this point to this, and you have to make this point to this. You have to make this point to this, and you have to make this point to this. So this is how we have to do it. So first what you have to do is you take P node next, means this I am modifying, equals to, suppose P node next equals to P current next, because we have P current next. That means what is happening here? So 1800 I am storing here. 1800 I am storing here. So P node next is made to point to this node. Next, P node previous equals to P current. That means this here we are storing 1200. So this is made to point to this. When we store 1800 here, this is made to point to this. So we have modified these two pointers. Now modify this and modify this. So what you do here is P node next, means still this one, P node next is 1800 of previous. No, that means I'm modifying this. P node next, previous of P node next. That means you are modifying this. You make equals to P node. This is not P node. 1 minute. So I want to modify the previous node of this. I don't have pointer to this. So how to get pointer to this is P node, P current next. P current next means I'm referring this node. P current next means I'm referring this node, and we have to set the previous pointer. So I have to say previous equals to P node. So when I say this, then assume that this is 2400. Now 2400 is stored here. Next, one more pointer we have to modify is this p current. P current next. P current next equals to p current next equals to p no. So that means here 2400 will be stored. So this is how we do the operation. So I have shown the manual operation. So you have to take care of both pointers, previous pointer and current pointer. So that is the reason it looks slightly complex. But if you draw the diagram like what I have drawn, then the problem will not be there. You can easily write this statement. So anywhere, any slightest of confusion, if you're finding, then draw the diagram. If you draw the diagram, the things will be sorted out. So there will not be any problem in writing the statement. So this is how we have to proceed. Similarly, suppose if I have to just delete a node, just one more I'll give. Just one more manual example I'll give before we proceed. So suppose if I take this, this is so this is suppose start. This is pointing to this, and this is pointing to this. This is pointing to this. This is pointing to this. Now suppose assume that this is 1800. This is 1000. This is 1200. Now 1800 is stored here, 1000 is stored here, then 1200 is stored here, 1800 is stored here. Now this is null and this is null. And there will be data here 10, 20, 30, some data will be there. Now suppose if I had to delete this node I have to delete. This is P current, I have to delete this node. So to delete this node, what I have to do is make this point to this. This should be bypassed and make this point to this. So we have to bypass this. Now this is free and we can delete this. We have pointer to this. Now first get this. How to get this? We have only pointer to this. To get this address of this, P current previous. So when I say P current previous, I'm referring this. Now I have to modify this pointer. So P current previous next equals to, I have to set this address. So what is, how to get this address? P current next. So P current next is 1200. Where I am storing 1200, I am storing 1200 here. That means this is made to point to this. Similarly, go here, P current next, P current next. That means I'm going here. I have to modify this, which is nothing but previous, equals to P current previous. P current previous is 1000. So this is 1000 is stored here. So when 1000 is stored here, now it is bypassed and it is stored. So now this node is bypassed and there is no link in the linked list. It is not part of that. So what I can do is I can release the memory area of this. I can say free P current. So this is how the operations we can do on doubly linked list. So I have just shown the manual operations. Now in C, suppose if I want to represent this, so again for every linked list node representation, we have to go for struct. So I'll take a structure here. So I'll take struct. So I'll take struct. I'll say doubly linked list D node. I'll say here int data. So one field is data, another field is pointer to the next node or previous, D node previous. So struct D node next. So this is how I had to do it. Then This is typedef. I told you in order to avoid struct each time, so I can say deno. This is how the node will be present. So there will be in singly linked list, there will be only next pointer. Now there is next pointer, there is previous pointer, there is data as usual. So this is how the node is represented. Now what we'll do is we'll write a program like single linked list. We can have the nodes, the insertion of a data item in the beginning, in the end, or after a given node. We can do all those operations that are done actually with single linked list. We can delete a node. Now, for a change, we can also do this similar operations and write a program. Now, what I'll do is instead of doing the similar operations, you can do the similar operations. There is no problem. Instead of doing similar operations, what I'll do is I'll maintain a doubly linked list in ascending order. Means the nodes of the doubly linked list will be in ascending order. Suppose if I have a node. Initially, I'm creating a node of suppose 40. Now I have to insert a node. Then I should insert before this. Before this, I have to insert. Next, suppose if I have to insert 30. So I have to insert in between these two. So this is how I want to maintain. So I don't want to have the similar program, slightly different program. So whenever I insert a node, I have to maintain the sorted order, ascending order of the data items. Similarly, when I delete, even if I delete, the ascending order should be maintained. And then we will have a sorting of not sorting because it's already sorted form. Traversal will have and search will have. So we'll have 3 operations, 4 operations. One is insert. So we'll not say insert begin, insert end, insert after a given like what we did with singly linked list. When we insert, it should be inserted at appropriate place so that the data items will be in sorted form, that too in ascending order. Deletion, so take a item, search for it. If it is found, delete, otherwise display message. Traverse means display all and search for a given item. So these are the operations we are going to have. So I'll write a program. So here, this is the program what we had. So instead of taking this, I'll rewrite the entire program. Only I'll take this. Better I rewrite the entire program. So I'll take only the struct here. So I'll say D node. So D node next. I'll say D capital. So let it be this, and I'll be having previous also. So I'll have previous node. So this is the node I want to have. Yes. This is the structure. So I'll go for main. Like I'll copy the main from here instead of writing, because the main is always with menu. So that is better. So the program, all data structure related programs will have main like this. So better I'll copy from here, that the time to develop the program is less. So I'll copy this here, int option here, D node. I'll say D node start, let it be item, let it be given. I don't require, because I'm always inserting in. So insert, only insert I'll have, one insert. 2 delete, 3 2 I'll have delete, 3 traverse, 4 search, 5 exit. So these are the operations I want to have. So enter option, enter data item to insert. So I'll say only insert, but start and item as usual. Then I'll remove. So delete, I'll directly go to delete. Case 2 is delete. to delete. So I'll say insert item instead of insert. I'll say insert item, delete item, enter item, start item, traverse. So this is 2. 2 is delete. 3 is traverse. 4 is search. So 4 is search, same I want to search. Then 5 is exit. 4 is search. So these are the operations. So I have taken I have taken here, if it is 5, I have to exit. So I've copied main from the earlier one. So I'll take insert and delete. Traverse also I'll have. Traverse is simple job. So first I'll write traverse. So void. So traverse, only one direction we can be doing. So traverse, same logic, whatever we have written for this is D node or first. So traverse. So I'll take D node P current equals to first, while this is same P current not equals to null. Then I'll say printf percentage D just arrow mark. I'll give P current data. This is traversal and P current equals to P current next. P current equals to P current next. So this is the traversal. So traversal is simple job. Next we'll say insert item. So I'll say void insert item because we have to modify the node. I'll say D node double asterisk first. I'll say pointer to first simply. It's first node and pointer to first. Then int item. So first I have to create a node as usual. First take a node. So take a node. I'll say D node pointer to new node P node. P node. I'll allot memory area dynamically. So D node typecast. Then malloc size of D node. So I'm taking allotting memory area. So the first special case we have to consider is suppose if it is empty. If it is empty, we have to. So what I'll do here is I'll take 2 cases. So first case is when node is empty. So suppose what I'm doing start is null, the first case. When I have to insert, second case is when the list is present. Assume that the list is present. So there is 10, 20, 30. This is I have to maintain the order. So 30. So this is the list present. So this is I have start or first whatever it is. Now I have to insert a node. Now insert a node. Suppose I have to insert some node. Insert some node. Suppose I have to insert 25. So I have to find a node which is just greater than this. Greater than this. So after that node, before that node, I had to insert. So when I find a greater node here, this is the node I'll find current. So what I'll do is I have to insert this node, because I told you we have to maintain the order. This is P node, new node. This is 25. If this is 25, it has to be inserted here. Now, how to check for this is, say, as long as this is smaller than this, proceed. This is P current, take P current. This is smaller, move P current to this. This is still smaller, move P current to this. This is okay. Now you have to insert in between these two. So to insert in between these two, it is easy. I told you the steps to insert. Even if you have, you need not maintain the previous node, because you can go to the previous node. So this is how we had to insert. Suppose by chance, if all the nodes are smaller than this, so it should be inserted at the end. So when all the nodes are smaller than this, it is inserted. It should be inserted at the end. So what we have to do is we have to maintain the previous node. Is it required? So what I'll do is I'll take a condition. If P node null, P node I have to insert as a last node. So I think we'll also have better to have even the last node. So I'll take the pointer to the last node also. Start and end node also I'll have a pointer. So that is, I think, better. So even without that also I can do. Normally it is better to have it. So I'll start from left side. We can do without that, but I'm thinking to have the last node also. Okay, we'll have the last node, so that because we can traverse in both direction, we can have the last node. When we have to have a last node, then so what we have to do is and keep on check here the node. Whether it is suppose if current is less than this, move this, current is less than this, move forward, and if you reach null, then it should be inserted as last node. It should be inserted as last node. So this is second. In second case, one special case is if you find a node, if you have to be inserting in between two nodes. So in between two nodes. This is one special case. One case in between two nodes. Now what I am doing, I'm taking P current. I'll also maintain here last or end. Start means I'll take last. Okay, start and last. So last pointer also I'm maintaining. So I'll start from left side and I'll say P current. As long as P current is small, I'll move smaller than the new node. I'll move P current to this. And once I find P current greater, I'll stop. Then I'll insert between previous node of P current and P current. Suppose if I don't find such node, then P current will be null. Then I have to insert it as last node. So this is the second case is it should be inserted as last node. Last node. And third case is suppose if I find the first node itself is greater than this. Suppose I have to insert 0.5. Find the first node itself. So when I find first node itself as greater, so insert as first node, So if first node itself is greater, then this should be inserted in the beginning. So this is how we have to do the modification. Okay. So this is how we have to do the modification. Yeah, I'll go ahead with this logic. So I'll take the last pointer also. So when I take the last pointer, I should also move the last pointer. So I'll take here start and also I'll take D node last goes to null. Then what each time I insert item, I should be passing both first and last. So last node also I'm passing. So when I pass last node here, I'll be passing the last node, D node pointer P last. So here the simple thing is check if first you check if P first is null. That is another special case that I told you when start is null. So start is null, last will also be null. If P first, asterisk P first equals to null, then it is the first node. So what I have to do is P node, I have to make this node the previous of this previous equals to null because it is the only node now. P node next, or I'll combine both. P previous equals to P node next equals to null. So both I'll make null. Then what I'll do is asterisk P first equals to asterisk P last equals to P node. So this is the node, and before that I had to move the data. So that is one important thing. I am not moving the data. P node data equals to item. So this is the first thing. So if both are null, so when both are null, what is happening in this case? I'm creating a new node. So new node is created. This is P node. P node. Now, when this is null, what I have to do is make this null, make this null. Both the previous and next you make null. Now there is last will also be null. Last will also be null. Now suppose assume that this is 2000. Make start 2000 so that start points to this. Make last 2000 so that last point to this. So this is the modification I am doing. One special case I am doing. P first equals to null. Then then it is the first node inserted. So I'm making previous and next null, and also I'm making both first and last pointer point to that particular node. So this is one case, and I need not proceed further. I can say return. This is one thing. Second thing, what I do is I have to insert. There is already list present. Now I have to insert. So first eliminate the special cases. Check whether the data is less than starting node, then insert it as a starting node. Greater than last node, then insert it as a last node. So that is a better logic, I think. So what I'll do is if P node data is less than or equals to, will eliminate this here. A duplicate is also allowed. P first. Then what I have to do is it should be inserted as first node. So when it is inserted as first node, so what is the case here is a new node to be inserted is first node. Suppose if it is 5. So 5 is less than this data. Now what you do is copy next to start, then make this start or null, make this null, and start you copy this. So these are the steps. So first you take P asterisk P first, means previous of P first, because it should be inserted before this. Previous of P first should be P node, new node. That means what I am doing, I'm storing this this one here. I'm storing this address. Suppose this address is 2000. I'm storing this here. This is first step. Second step is P node next. Sorry, P first previous. Yeah, P node next. P node next equals to P first. P node next equals to P first. That means now P first, this is start is having start, suppose this is having 1800, this is the 1800. Now I'm storing 1800 here so that this points to this. So that is the second step. Next, what we have to do, we have modified two pointers. Now modify the previous of node, current node. See here, what I'm doing is I'll redo this. So I'll explain it neatly. So start, assume that there is 1800 here and 1800 is stored here. Then I have created a new node and the value of the new node is less than this. Now what I'll do is I'll first modify the current node. That is better. In a proper way I'll do it. I'll keep this ladder. So first I'll modify the new node addresses. P node, I'll make P, this is P node. This is P node. Assume that this is 2000. Now P node next equals to start. Start is 1800. I'll copy this. I'll copy 1800 here so that this will be this. And then what I'll do is I'll copy previous node null. I'll copy previous node null. So that is one more thing. So what I'll do is P node, because it is the first node, previous node of first will be null, previous equals to null. So I have modified both these pointers. This pointer I have modified. This pointer I have modified. This pointer I have modified. Now I have to modify this pointer. This pointer should be pointing to this. So what is this pointer? This is pointing to this. So what is this pointer? Start previous. Start previous. So when I take start previous or first previous, P first. Yes. P first previous equals to P node. So what I'm doing here, into this here, P first, this is P first previous is this one. I'm storing 2000. Now this is no more first node now. So start or first should be 2000. That is one more step. So here what I have to do is last thing is asterisk. Last thing what I have to do is asterisk P first equals to P node. That means the new node will be the first node. So these are the steps if I have to insert as first node. So inserted as first node. Inserted as first node. This is the step. You have to be very careful in writing the code because the code is slightly complex. Now this is okay. Else, suppose if it is next other possibility, what I'll check is else if P node data P node data greater than P lost data. P lost data means it has to be inserted as last node. It has to be inserted as last node. In this case, so I have to insert here last node. This is the last node. Suppose this is 30, I have to insert 40. This is P node. Now, as usual, first modify P node. So you say P node next. So P node next will be null because it is the last node. It is going to be the last node. So that is one thing I am doing. P node previous should be pointing to this. Suppose assume that this is 1200. So 1200 I have to copy here. So I have modified first P node details. So I'll say asterisk P node P node. Sorry, this is P node next. Yeah, P node next. P node next is null because it is going to be the last node. Then P node previous should be the last node. The last node. So I have done the two modifications. Now the next thing is this node here. Earlier it was null. I have to make it to point to this. So how to get this? To get this, what I have to do? I have to say last next. So last next is P node because it is going to be the last node. So that is one more step. So asterisk last next equals to P node. Then now everything is modified. Now this is no more last node. Last now should be pointing to this. So what I have to do is last equals to asterisk last equals to P node. Asterisk last equals to P node. So that is one more thing I have to do. So this is P node. I think last instead of last I have taken P last. So just some change in spelling here, P last. Now P last, this is also P last. Next, asterisk P last equals to P node. So I have modified the last node will be the P node now. That is the modification I require. So every place 4 pointers are modified. Each time 4 pointers are modified. These are the special cases. I have considered 3 special cases. One is when list is empty. Second is when the new node to be inserted. Here my requirement is to maintain this sorted data. So that is my requirement. So that's why the logic is different. I can write insert at beginning, insert at end, insert in the middle, but I want to write with different purpose. The purpose is I want to maintain a linked list of sorted data. So in ascending order, that's why I'm doing this. So if it is null, I have to make that node as first node and last node. If it is if it is not empty, then check whether new node is less than or equals to first. If it is less than or equals to first, insert it as a first node, or new node is greater than last node, then insert it as a last node. So this is here it is inserted as last node. Inserted as last node. Inserted as last node. Then if it is not empty, not first node, not last node, then it must be somewhere in the middle. So find out the position where to insert. Find out the position where to insert. So that is the last case and general case. So I'll take one more here so that it will be clear. So I'll take here one node, another node, third node, just 3 I'll take. So this is assume that this is 15, this is 50, this is 80. Now this is pointing to this. 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 This is null. This is null. Now the node, whatever we are inserting, because special cases are done, it must be suppose assume that this is 60. So to find its position, check the node whose value is as long as find a node whose value is greater. So 15 greater, no, 50 greater, no, 80 greater. Then you stop. Then when 80 is greater or equal, then I have to insert this node in between these two. So what I'll do is I'll take P current and I'll keep on find a node whose value is greater than this. So once I find a value greater than this, then greater than this, then I can insert the node before that. So that is the logic, the last case. So insert somewhere in the middle. This is insert somewhere in the middle. So this is somewhere in the middle. So what I have to do here is I'll take P current. P current equals to P start. I'll start from, sorry, D node. I have to declare here. I cannot declare there. I'll declare here. I can also declare that. Better, I'll declare here P current. So what I'll do is I'll take P current. P current equals to asterisk P first. Now while P current data less than data less than P node data. So as long as it is less, I'll proceed. Once I find greater or equal to, I'll stop. So this is the logic. So I'll say P current equals to P current next. So I'll till I reach a node which is greater node, I'll be proceeding. So now 60 P current is here. This is less than this, then I'll proceed here. Less than this, I'll proceed here, not less. Then I had to stop and I had to insert before this. So that is the logic. So there is no possibility that this is going to be null, because suppose if it is greater than this, we are already taken care here. So there is no possibility that P current is going to be null. There is no possibility that P current is going to be null. Okay, so that is the reason we can proceed. I need not check any special condition. Now we have reached here. P current is here. This is P current. This is P node. Now I have to modify, as I told you already. Now first modify this, make this point to this. Then modify this, make this point to this. So first I'll do those two. So how to do that? I'll say P current next equals to, sorry, not P current, P node next equals to P current. So this is where now P current is here. Now I have to make P node next point to this. So P node next equals to P current. This is one thing. P node previous equals to P current previous. So how to get this one? This is P current. Assume that this is 1800. 1800 will be stored here. So P current previous will be 1800. So that 1800 P current previous is 1800. That 1800 I am storing here. Now assume that this is 2000. P current is 2000. I am storing 2000 here. So now P node is modified. Now I have to make this node point to P current, and next of this node point to P current, and next previous of this point to this node. So what is the step? P current previous next. So previous node of current node should be pointing to P node. Then P current previous should be pointing to P node. This is the logic. So this is insert logic. So we have done insert logic. Now I'll execute the program, because we have done traverse and this logic. So traverse, I think remaining delete item have not written. So just I'll make this comment because I have not written. Just I want to check whether this is working fine or not. So I'll execute this. This is doubly linked list operations. Doubly linked just .c. So what is the error? Request for number data is something. structure. So asterisk p first data. Denote start. This is start last. So we'll check what is the error. Denote p first, denote p last. Okay, it should be correct. Then what is the error? P first data. So what it is saying, request for member data in something not our unit structure on here. So I think I'll take this way. I'll try to execute this. Yeah, it is fine now. So wherever this is used better, because there is some precedence problem. So I think that is the problem here. Take this here also the same thing. Okay, now I'll execute. So expected semicolon here. Okay, now I think it's okay. So I'll insert 50. Now I'll try to display. So 50 is displayed. Again insert. I'm not saying where to insert. Based on the value, it should go to appropriate place. Enter option. Suppose if I say 20. Now if I say 3, so 20, 50, correct. Then again I'll say insert. Now I'll say 70. So again I'll say 3 traverse. So 20, 50, 70. Again I'll say 1. Now I'll insert in between. So I'll say 60. So 1, 5, sorry, 3 traverse. So it is coming fine. Then I'll insert one smaller value like 10. So it should come first. So again traverse. So 10, 20, it's working fine. Then last I'll try one more. 25 I'll insert. It should go to appropriate place. So 3. So it is going to appropriate place. So insert is working fine. So I'll try to insert last before one more option. So 65. So 3. So it is working fine. So insert is working fine. It is displaying the data at appropriate. It is keeping the data item at appropriate place. Whenever you insert, it will move that data in our move that data into the doubly linked list in such a way that the items are in sorted order. So that's what happening. So it is working fine. So insert we have seen and traverse we have seen, both are working fine. Traverse is to check to display the data item. So it is working fine. Next we'll see delete operation. So this is the insert operation. I'm taking care of some special cases here. First is when the list is empty. So that's what you have to do. Wherever there is a possibility of a special case, if you need to treat it separately, because if you don't treat it separately, then the logic, there will be a problem. So you have to consider each special case here. One special case what I'm considering is when list is empty. List is empty, one special case. Case is when the new node needs to be inserted in the beginning. Third special case is when the new node is to be inserted at the end. The last one is a general case. It should be inserted somewhere in the middle. So it is working fine. So we have completed the insert operation related with doubly linked list. Next we'll see delete operation. So I'll say delete item. Again, we have to pass start and last because both we require. So and last. So item to be deleted. So I'll take delete item, void delete item. So we require a D node P first, D node P last, then int item. Now suppose this I'll close it, 5 exit, I'll close. Here in traverse, what I'll do is I'll just have one new line so that it will go to the next line after printing. So just after this, I'll say printf. Now I'll take one example. So this is the node to be deleted. So this is assume that this is 10, 20, 30. Now what I have to do here is I have to search for the node. So I have to delete suppose 25. So what I have to do here is 25 compare with this not matching, compare with this not matching, and compare with this. You have to stop as soon as you find a node which is greater, because there is no possibility that there is a possibility that 25 will be present after 10. There is a possibility that 25 will be present after 20. There is no possibility that 25 is present after 30. So you need not exhaust a list to say that it is not available, because it is in order. As soon as you find a greater node, stop and say that it is not matching. So that is one thing you have to do. Second thing is, if it matches, suppose if I had to delete 20. So if I had to delete 20, suppose it is somewhere in the middle. So what statements I have to write is, this is the P current node. It is the node to be deleted. It is matching. If it is matching, this is P current. So now I told you this should be bypassed. So this should be bypassed here, and this should be bypassed here. So to bypass this, take this node and assign this address. Suppose assume that this is 1800, this is 1200, this is 1600. Now this is 1200 will be present here, 1800, this is 1200 will be present here. Now this is 1800 is present here and 1600 is present here. Now what you have to do is go here and assign 1800. So how to go here? P current previous. So what P current previous I should have? I should have P current previous of next. So this is P current previous. P current previous is this one. But I don't want to modify P current previous. P current previous is this one. But I have to modify next of P current previous. So next of P current previous is P current next is. That means 1800 I have to store here. 1800 I have to store, so that this is bypassed. So P current next. Similarly, take this so that you will follow. So this will have 1200. This will have 1200. There is 1600 here. There is 1800 here. Now I have to modify this pointer. To modify this pointer, first go to the node. How to go to that node? P current previous. When I say P current previous, I am reaching this node. But next node of this node I have to modify. So I have reached here by saying P current previous, but I have to modify next node of that. So P current previous next equals to, here what I have to store? 1800. Where I get 1800? 1800 is available here. So this is equals to P current current next. So P current next 1800 I'm storing here. So now this is overwritten 1800. Now this 1800, 1200 is overwritten with 1800. That means from here now I am bypassing 1200 directly going to the node with 1800. Okay. Similarly, I have to modify this position. How to first modify this position? First go here. To go there, I have only one option, P current. So how to go there? I'll use P current. P current next. When I say P current next, I'm reaching here, but I have to modify the previous of next. So previous. So what I have to store here in previous 1600. Where is 1600 available? It is available here, which is nothing but P current previous. So when I do this, now this node is bypassed. This node is bypassed and it is modified. Okay. Now, one thing here is suppose this is working fine if it is in the middle. Suppose if the node to be deleted is the first node. Node to be deleted is first. Now P current will be here only. If it is P current is here, now P current previous will be null. So this will cause error. When the node to be deleted is first node. So I have to take it separately. Similarly, when the node to be deleted is last node, P current next previous will be null. So, sorry, P current. So when the node to be deleted is last, this is last, P current next is null. So this will give error because there is no next node present. So this logic will work fine only when if it is in the middle. So I cannot use the same logic if the node to be deleted is first. So this will work fine only if it is in the middle. Suppose if it is node to be deleted is first. So if node to be deleted is first, then I'll take another case here. Suppose if it is 10. So this is I have to delete this node. When I have to delete this node, I'll take one more diagram better. So this logic, whatever I'm writing, work fine if it is somewhere in the middle. If the node to be deleted is first, this will fail. If node to be deleted is last, it will fail. So we'll take the cases where node to be deleted is first and node to be deleted is last. So what I'll do is I'll take this. I'll take this. Take this. So this is pointing to this, this is pointing to this, this is pointing to this, this is pointing to this. Assume that this is 10, 20, 30. Now this is first and this is last. This is last. So what I have to do is suppose if node to be deleted is 10, node to be deleted is 10. So it is matching. So it is matching with the first. So what I have to do is I have to bypass this. To bypass this, you take the next node of first node. Next node of first node. Now one more thing before that what I'll do is I'll take one special case where there is only node to be deleted. Suppose there is only node 1 present. I have to delete this. That means if this is first and this is last, then I have to delete in a separate when only node to be deleted is there, then I have to simply make first equals to null and last equals to null. So this also I'll take that special case. So first I'll write that. So delete item. First check if first thing is P first is null. Asterisk P first is null. Asterisk P first equals to null. If it is null, then list is empty. We have to return nothing. It cannot be deleted. So list is required node not found. I can say required node not found. So printf required node not found. That is one thing I have to write if the list is empty. Suppose if I have to delete the node, if asterisk p first data equals to asterisk p last, because both are same. Data equals to item. So there is only one item to delete, and that is then in that case what I have to do is I have to take p current. I'll say d node p current. I'll make equals to asterisk p first. So I'll make what I'll do is I'll say asterisk p first equals to null. Asterisk p equals to null. Asterisk p last null. Both I am making null if it is the only node to be deleted. Next, suppose if it is the first node to be deleted. So this is when both are matching. Suppose if both are not matching, then the special case is if asterisk p first data equals to item. If this is matching, if it is the first node, what I have to do is, so there is this is the case I have to delete. Then what I have to do is take this node. How to get this node? P first next. P first next is I'm going here, and previous of that you make it null. Previous of that you make it null. So that is one step. That is one thing I have to do. P first asterisk p first asterisk p first next previous so asterisk p first next asterisk p first next previous previous asterisk p first next previous equals to null. That means because it is going to be first node now. Next, this is going to be first node because I'm going to delete this. Now, first you make it to point to this. So that is what we have to do. So you make first asterisk p first to asterisk p first equals to asterisk p first next. Asterisk p first next. So the next whatever next node available here, that we are making it to point to this. Now this node is free. So this p first I'm making it to point to next. Suppose if this is 1800, this is p first next. This there will be 1800. Now assume that this is 1200. So now first what is there in first is 1200. So what I'm doing is P first means this node, next 1800, P first, sorry, P first, next 1800. That means now this 1800 I'm storing here. So when I store 1800 here, first will be pointing to this. Now this node is bypassed. This node is bypassed. So this is when the node to be deleted is the first node. Similarly, when node to be deleted is the last node. Else, oh, else, this I'll say return. Here I'll say return. It is here also I have to say return. Is it written? P first? No, not written. I have to do that. Then I'll say else here, else. Then one more else if here is. One more else if here is. See, only this program is slightly complex. Remaining will not be this much complex. So when P first, this is not P first now, last, P last data is equals to item. Then what I am doing, I have to delete this node. I have to delete this node. So when I have to delete this node, then what I have to do is I have to make this node null. This is null. How to make that null? So last previous means I'm reaching here. Then next I'll make it null. Then last I have to make it to point to this. Last equals to last next. Last previous. So this I have to do it. So last here. So P last previous. So wherever there is next, I'll say previous, and wherever there is previous, I'll say next. Then here P last to P last next. So this is matching here. What I have to do is because I have to delete the last node, so I should say P current equals to P last, because this is the node I have to delete. P current equals to P last. That node I have to delete. So I'll copy here. So this is another special case when this is one special case here is when list is empty. List is empty. Case is when only node to be deleted is only node. So this is another special case. There is only one node and we are deleting. And this is node to be deleted is first node. Node to be deleted. First node. Then this is node to be deleted is the last node. Node to be deleted. So all special cases we have considered. Now what I have to do is I have to search for the node. So else, if no special case is matching, I have to search for the node with the help of P current. P current I have already assigned, while P current data is less than item. If it is less than P current data less than item, I'll move the P current. So I'll move P current. So I'll say P current equals to P current next. That's what I told you, the logic. Now come out of the loop. If P current data is greater than item, then the required node is not found. So I'll say I'll say p current data greater than item. I'll say printf required node, or I'll say that item is not found, required node with value %d. %d here is item is not found. Same message I'll keep here also. So I'll keep here also. So I'll say not found. Then I'll not do any deletion. So suppose if we reach here, then p current will be having the node to be deleted. So I'll say printf. I'll keep that printf statement. Required node with value is deleted. If we reach here, it is deleted. Then we have to say free p current. This is the logic to delete. Now we'll check whether it is working fine or not. I'll execute. So what it is saying, error unknown, type name D node, here capital I had to give. Yeah, that is the reason why it is not. Okay, now it should work fine. So again, that I had to write here, P first. Then also this I had to write. I think it's fine now. Yeah. Sorry, I should keep asterisks inside. So now I think it should work fine. So it's okay. First I'll insert. So I'll insert 25, then insert 15, insert 45, sorry, 1, 45, insert 50. So now I'll check whether, so 15, 25, 45, 50. Now I'll delete some item in the middle. So I'll delete 20. I'll first try to delete the item which is not there. So I'll say 40. So required node with value not found. It is giving fine. Now I'll try to delete the node which is in the middle. So I'll delete 25. So required node with value 25 is deleted. So I'll check whether the data is maintained properly or not. So it should be. So what is for 25? It is deleted. Now 15, 45, 50 should be displayed. So I'll say traverse. Oh, there is a mistake. So that is the problem. So there is something wrong happening. So that is why I'm doing all possibilities. The node to be deleted is in the middle. It is giving some error. So I'll check what is that error. So P current equals to asterisk P first. Suppose if data P first data, okay, then P, while P current data less than item. So less than item, less than item, if it is there, once it is greater or equals to, it will stop. So 15, 25, once it is 25 matching P current data less than false. So it will stop here. If P current data greater than item with value not found, it says, it is not saying that. Then required node with value is deleted. Free P current. I think we have to modify the pointers. That I did not do. Sorry. Here the important thing is when it is somewhere in the middle, I have to write these statements which I told you. The statement we have to write is these statements I forget to write. So if we write that, it works fine. So here, if it is matching, then it will come here. So what we have to do is p current next yes equals to p current previous. So that is the problem. Then p current previous next equals to p current next. Is that p current previous next equals to p current next, p current next previous equals to p current previous. Yeah, it is fine. Now it should be okay. It should be okay. What it is giving some warning ID. Oh, okay, this I should close. I'll close this. I'll close this. Now I'll execute. I think it should be okay. So I'll insert. So I'll insert 11. I'll insert 55. I'll insert 22. I'll insert 44. Okay. I'll check. So 11, 22, 44, 55. Now I'll try to delete item which is not there. So I'll say 40. So 2, 40. Required not found. So I'll see the data. So it should be as it is. Now I'll delete 22. So 2, I'll delete 22. So deleted. Now I'll check. So it is coming fine. 11, 44, 55. So now it is fine. Now I'll delete the node which is in the beginning. So I'll delete 1. Sorry, 2 to delete. First node I'll delete. So required node with value is deleted. Now I'll check traverse. So 44, 55. Now I'll delete the last node, another special case, 55. Now I'll check whether it is working fine. So fine. Now I'll delete only node present. So delete 44. Only node present. Enter data to delete item 44. What it is doing. It should. I had to remove that node. So that is okay here. P first node. P node next equals to P current next. So then, sorry, delete. I have to come here. If it is only node to be deleted, P first equals to P last equals to null. So P first data null. Then where it is coming else, it comes here. Free P current. P current equals to P first data equals to P last data equals to item. P first asterisk P first data equals to P last data equals to item. Then P asterisk P first equals to asterisk P last equals to null. So it is correct. Then what it is required node with value percentage D is deleted. Then when I traverse here, traverse what I am doing, traverse 44, when I delete, it is coming here. First not null, asterisk first data. Okay, I'll execute it again. So I'll insert 1, suppose 10, 3. There is only one node. I'll try to delete that. Now we'll see what is happening. So it is coming out when we delete. What is the problem here? P asterisk P first data equals to asterisk P last data equals to item. So asterisk P first equals to null. What I'll do is asterisk P, I'll check this way. P first data equals to item. Oh, I have to use and, that is the problem. Okay. equals to item. So I'm using some wrong technique here, and asterisk p last equals to, so that is better. Asterisk p last equals to asterisk p last equals to asterisk p first. Now it is fine. It should be fine. There is no problem. So asterisk p first data equals to item, and asterisk p last and equals to asterisk p first. Now I think it is fine. So I'll execute this. It should be okay now. So I'll insert 1. So suppose 10, 3, 10. I'll delete the same one. So it should be okay. Now it is working fine. So if I try to display, nothing comes. So 1, I'll say 10, then 1, 50, then 1, 20. So I'll display everything. Now 10, I'll delete the last node. Now it is, everything is working fine. So 2, last node I'll delete 50. Now I'll display 3, it is working fine. I'll delete the first node 10. So if I say 3, I'll get 20. I'll delete the only node present. Now it is working fine. So delete only node, enter data to delete item 20. So it is deleting. P first data equals to item, asterisk p last equals to asterisk p first, asterisk p first equals to asterisk p last equals to null. Yeah, it is working fine. Asterisk p current dnode asterisk p first data equals to item, and asterisk p last equals to asterisk p first. That means only deleted, so it is working fine. Int item, I'll execute this again. So insert, what I am doing, if p first asterisk null, p node previous, p node p node previous equals to p node next equals to null. Next, when I delete p node asterisk p first data equals to item, and asterisk p last equals to p first. Asterisk p first and p last are same. So I'll try to execute it again. So 1, insert 25. I'll try to delete, I'll say 3. So I'll try to delete that 25. So it required with value node 25 is deleted. It is working fine. So it is deleted. So here p first, else if printf required node. So when it is found, node with value not found item. So required node with value is found. I'll say printf only node. I'll execute it again. So I'll execute again. So I'll insert 1, I'll insert 11, insert 22, insert 33. Now I'll display, I'll delete first node 11. So 3, I'll delete last node 33. Then traverse, I'll delete the only node present 2. When I delete only node present 22, it's coming out. Enter data to be present. So here the time 37. Okay, why it is coming out? P first equals to null, required p current dnode p current equals to p first. P first P asterisk P first equals to asterisk P last equals to null. Node deleted. P last equals to null. Asterisk P last equals to null. We'll see this way. I'll execute. So 1, 11, 1, 22, 1, 33. So 3, delete last node, 33, delete first, now 3, delete first node, 11. Now traverse 22, delete 2, 22. This, when it is only node, why it is not coming? Asterisk P last, asterisk P first equals to null, asterisk P last equals to null. P first equals to data, asterisk P first data equals to item, and asterisk P last and asterisk P first. A modification somewhere mistake, P last, P first equals to P last, P node, P first equals to null, asterisk P first equals to P node, asterisk P last equals to P node, P node, asterisk P node. When it is less than this, asterisk P first equals to P node. When it is greater than this, asterisk P last equals to P node, previous, null, next, null, next, P last. So P first, P data less than P node, P current, delete item. Okay, I'll try again. So somewhere slight mistake is there. We have to check that. Insert item 11, insert item 22, insert item 33. So traverse, delete 11, traverse, delete 22, traverse, delete 33. Yeah, required node with value 3 is deleted. Only node is deleted. Required node with value 33 is deleted. So now it is working fine. Now when I say 3, it is giving. So required here, what it says is only node is deleted. And here it's saying, okay, it is working fine, I think. Okay, I'll go back here again. I'll execute this. One more possibility I'll try. It is working fine now. So I'll execute it again. I'll close this. So I'll execute this. So 1, 11, 1, 22, 1, 33, 3. Then I'll delete first node 11. I'll delete last node 33. Then I'll say there is 22. I'll delete 22. So it is last node. If I delete, so if I delete last node, there is, I think, problem. So somewhere some pointer modification I'm not doing properly. So if delete last node, if P first data equals to item, else if P first data equals to item, then asterisk P first next equals to previous, P last previous next equals to null, asterisk P last equals to P last. Oh, here there is a mistake. This is the mistake. Now it works fine, surely. So that is the mistake, some copy paste mistake. Now it works fine. So 11, 1, 22. Sometimes finding mistakes is very difficult thing here. Now it works fine. 2. So I'll delete whatever I delete now I should get. So 11, now I'll say 33. Now delete last node 33. Now 3, delete the first node, the only node 2. So 22. Now it will work fine. There is no problem. So this is the final logic. Now it will work fine again. Now if I try to, there is nothing. If I try to insert now again, I can build from the beginning. So 150, 145, 122. Now we'll check 3. So we can delete any node. Now it works fine. So I'll delete 45 to 45. Now 3. So it is, I'll delete 50. So 250. Now if I say 3, so it is 1022. I'll delete first node 10. If I traverse, so it is 2, then delete 22. Now it is working fine. So this is the logic. So finally we are able to see, sometimes it is very difficult to find the errors. So you have to be very careful. So debugging is very difficult process. So while writing itself, you have to be careful. So I did a mistake here. Instead of when last item to be deleted here, I did a mistake. So this was next. When I copied here, this next should be changed to previous. I did not do it. So that is the mistake. So now I think it's fine. So it is working fine. This is the program. So go through the program carefully. See, programs in data structures will be like this. But if you understand the concept and draw the diagram properly, so then you can write it. But you have to be careful because anyhow, we are humans. When we write the program, every step we have to carefully write. And here one small mistake was creating problems. So it is always better if you do the mistakes while you develop, you can know where you are going wrong. Then next time you will not be repeating it. So this is it's a slightly complex program because doubly linked list, maintaining sorting order and deleting. So it is slightly complex. So anyhow, we are able to find the error here and we could correct it. So